Okay, thank you for joining us today, and I will be talking to you about my project, which was assessing aspect control on weathering within 2 adjacent hill slopes on the Boulder Creek Critical Zone Observatory, and this was employed using seismic velocity models. So there are multiple processes on the Earth that have been studied by scientists for years. However, there's still not a lot known about how the Earth's outer skin works. And this outer skin is classified as a critical zone. It contains the air, the trees, the soil, the water, and rocks that change with time on Earth. And one concept that is used is north-facing and south-facing slopes. So to just clarify what that means is when I'm talking about north-facing slope, you are in the shadier side of the slope that tends to not receive as much sunlight as the south-facing side. During the year, it tends to remain cooler, as well as keep snowpack on that side during the winter time. Now, on the south-facing slope, this side receives more sunlight and stays warmer throughout the year. During the winter season, it receives more of a freeze-thaw episode rather than the continuous snowpack. So previous studies that have been conducted on hill slopes within an area called Gordon Gulch was done by Beefus in 2011, and what he had concluded through shallow seismic refraction method is that the north-facing side is deeper in weathering than the south-facing side. Now, there's also velocity models that have been reproduced to replicate over 1 million years of freeze-thaw episodes. This was done in 2013 by Anderson et al. And what they had found is something very similar. The south-facing slope would have a shallower depth to weathering than the north-facing slope, which should be thicker. Now, a recent study actually shows that the depth to weathering on both the north and the south-facing slopes would be parallel rather than the north-facing being deeper than the south-facing. So this was done by using seismic velocity models as well as electrical resistivity. And again, St. Clair is the one who had contributed to this. So the particular field area, when I'm talking about Gordon Gulch, this is in an area called the Boulder Creek Critical Zone Observatory, and this is in the Boulder Creek watershed. There are 3 main areas that are studied within here. However, Gordon Gulch is where I'll be focusing on. Again, that's west of Boulder and just north of Netherland, outlined in yellow. So what we have is our area, which is the upper Gordon Gulch, and our south-facing and north-facing slopes both have 2 survey lines on each that we conducted for our research. And that can be seen by the green asterisks. And how this was done was through the seismic refraction method. And what that contains is we must have a seismometer by geometrics. It's connected to a computer that's able to gather the seismic waves, and a trigger-activated hammer that produces the seismic waves, as well as geophones that are placed within the ground. We had 23 spaced every 1 meter. So what that does is it records all of the waves that get propagated back through. This is all connected to a 12-volt battery. So what you see is, again, the geophones on top. The seismic source, or the trigger-activated hammer, is struck against a steel metal plate that produces seismic waves throughout the ground. We get 2 types. We get reflected waves and we get refracted waves. The reflected waves are the first wave arrivals that are recorded by the geophones. The refracted waves do go along the bottom border of between V1 and V2, but it must propagate back up through the first material, so it could slow down. Now, how does this look? Well, I'll show you. What we have here is hammer stack, and what a hammer stack is just a repeated measurement, so it's done over and over, and we had done 4 on each spot, so it's every 2 meters we struck 4 times.
Good.
And here what you see is the seismic lines being produced by the trigger-activated hammer. Unfortunately, you don't see the fourth hammer stack, but once that's completed, all the seismic lines do come together so that we be able to reduce unrelated seismic noise and get the maximum magnitude of the seismic signal. So this leads into seismic anisotropy. And what is that? So seismic anisotropy is the directional dependence of seismic waves as it propagates through rocks, and what we were determining is the fracture direction. So how this is done, again, the shallow seismic refraction method is a near-surface geophysical method that uses seismic waves to be able to classify the geologic framework of the subsurface. And how we had done this, again, we had used 4 survey lines, and for each survey line, we had them placed perpendicular and diagonal to one another. So the 30-meter lines, we pivoted on one geophone in the middle. Again, this is to get the V1 and the V2, or the direct arrivals and the refracted arrivals. So you may ask yourself, but why? Why is this important? Well, I'll tell you why seismic anisotropy is important on adjacent hill slopes. Most important is groundwater. Understanding where it is within the subsurface and the holding capacity of these hill slopes is important to understand how the rocks are broken down. So we have the main bedrock that's broken down and weathered into saprolite. That's also weathered into regolith. Now, as I stated before, the critical zone is the zone that's from the groundwater up to the top of the nearest canopy. It can range anywhere from 1 meter to tens of meters. We don't know the exact thicknesses, so this is part of the project that we're working on, is finding how thick these depths are. Now, this ultimately leads to soil composition on the adjacent slope. So if, for example, everything was heating up, as Deanna had mentioned, then everything changed the soil composition on the slopes. If the north-facing side doesn't have enough snowpack and the rock doesn't weather down as much, it would change the composition of the soil, which could ultimately alter the sustainability of the ecosystem. So as you can see, one hammer stack can give you a full 2D representation of a dinosaur. This is in 1993, according to Jurassic Park. Now, this is 2015, and this is what geophysicists really see. What we have here is we have time versus distance. So we have those hammer stacks and those seismic lines that are recorded by each geophone, and what we have is a shot location pointed, outlined here with the red star. What we had to do is actually collect and manually pick the first arrivals, or the P waves, each trace, so that we were able to find our travel time curves. And how this really helps us is understand the velocity of the seismic waves. So on the left here, we have the direct arrivals, or the V1, and we distinguish that with the break in the slope outlined with the black line in the middle. Now we have the apparent V2 that appears to be slower than the first arrival, and so we classified that as the reflected arrivals. And again, it does slow down because it has to propagate back up through that material. Now, for us to actually calculate the velocity, we had to take the inverse of the slope of the linear regression of that line. So after that's all completed, we get our results from the time travel curves. And this is actually plotted in something known as a polar plot. Now, a polar plot is something that shows magnitude and direction. So we have velocity in meters per second, and on each one of these graphs, you'll see 500 increments, as well as respect to north, south, east, and west, or a compass-bearing point known as an azimuth. What we have here, for example, V1 is below 500 meters per second, and it doesn't appear to have any preferential direction. It is isotropic. It is more of a circle. Now, for example, our V2 gave us more than interesting results. We can see that the velocities are faster at about 1,400 meters per second, and preferential direction is in east-west. So this is really good. Now, as I said before, we did have 4 total survey lines. You know, it's kind of a lot to look at, but what this is broken down into is that the V1s are on the left and the V2s are on the right on each graph. The V1s indicate that they are all isotropic. They are at or below 500 meters per second. And with V2, it indicates on 3 of the 4 surveys that they are in the east-west direction. So that just indicates the fractures are in the east-west direction. Now, the first survey, I'll go over why we might not have seen anything in a minute. So, again, back to the original question, what's going on? We have Beefitz here who says that the north-facing slope should be shallower than, or it should be deeper than the south-facing slope. And then we have St. Clair who says that it all should be parallel. Now, our results indicate there are variations in seismic anisotropy. The V1s all tend to be at or below 500 meters per second, very isotropic, so it's very continuous to an unconsolidated regolith material. And we also, with V2, it appears that it's more of a compacted, fracture-oriented material. So that would be similar to saprolite. Again, the velocity at approximately 1,400 meters per second on average. And so, as I stated before, the first survey that we had actually conducted was on June 16th. And as you can see in our precipitation graph of this year, on the 16th of June, we did see a spike in precipitation that day. So what does that mean? Well, studies have shown that velocities do travel faster in the direction of fracturing, but it can decrease with increased saturation. What does that mean? It means that if the fractures are filled, that means we can't get the anisotropy within those fractures because they can't be read by the machines. So that could explain why we didn't get anything that day. What does that mean? So there's still a lot known about the depth to weathering, the north-facing and south-facing slope. And it could still mean that Beefitz and Anderson are correct, but not sure. However, what we do know is that seismic anisotropy can be determined on adjacent hill slopes if conditions are dry. Now, we do need to have future work to be able to see further into the surface. For us to be able to do that, that could include further spacing out the geophones larger than just 1 meter. And we could also employ a new technique, which is ground-penetrating radar infiltration experiments, so that we'd be able to see where the water is and determine where the flow is. So I would like to thank my mentors and everybody who was a part of this process, and yes, especially Aisha. So. Okay, is there any questions?
All right, thanks, Stacy. Oh, great job. Do you have any questions?
Did you, on the slopes that you looked at, were the slope angles equivalent?
The slope angles, so there have been borehole data that was done previously, and they're actually working on right now correlating the borehole data with our information. So that's still, we're still finding that out, but yeah, it appears to be.
Hi, Stacy. Nice job.
Thank you.
What distance would you recommend spacing the geophones apart in the future?
Well, I would try 2 meters. Are certain spacings that will allow you to get to a certain depth. That could approximately be 20 meters. It depends on the area, so that's what I would recommend.
Okay, I'll ask a question too, but forgive my unfamiliarity with the topic.
That's okay.
So you're looking at the depth to weathering, and is that the same as effectively the depth to bedrock?
Yes.
The thickness of soil profile?
So that's ultimately what we're trying to find. Our survey only went to the first top 2 layers. So you have the regolith, which is very loose, unconsolidated, then the saprolite, which is the weathered bedrock that hasn't moved, and then the bedrock. We didn't get down to the bedrock. We got to the top of the saprolite. So yeah.
Are all these soil profiles, are these residual soils that developed effectively originally on bare bedrock? I guess what I'm wondering is if the depth to soil profile doesn't really have as much to do with the north versus south intensity of weathering, but maybe, if this is if there's a lot of till there, if it's unconsolidated material, maybe it's more associated with removal of that stuff on the south side as opposed to deeper weathering on the north side.
Right. So the south side, because it's steeper, it could cause it to weather faster.
Oh, it is steeper too? I was thinking more, maybe there's more water going through it or something. I don't know.
All right, no more questions? Thanks, Stacy.